So for hyperbolic equations, let's look at what is special for this case. What is special is kappa is equal to 0. So the rate of diffusion here is equal to 0. And when that happens, the equation becomes partial W, partial T, plus our original big U, partial W, partial X is equal to 0. Right, so there is no second order derivative anywhere anymore. So what's special about this equation? Now this equation has a name called hyperbolic equations. So these are the three type of geometric entities that kind of is analogous to the three type of equations: parabolic, elliptic, and hyperbolic. What's special about hyperbolic equations? Again, if you draw a diagram of t and x, and if you put a right-hand side, if you put a delta function of x minus x0 and t minus t0 over here, and suppose this is x0, this is t0, what is going to change in here? Any guesses? Well, first let's I'm going to launch MATLAB and do the same demo as we did last time, but like with a kappa equal to 0. Meanwhile, you can imagine, think what we saw last time. If kappa is equal to 0, how the solution is going to evolve. And maybe that's going to give you answer to the question I was just asking. What is the domain of influence for a purely hyperbolic equation? Let's go back to here. So convection diffusion equation, let's set the velocity to 1 and kappa equal to 0. Okay, now let's imagine our delta function we set, let's imagine our delta function is at t equal to 0. So adding a delta function here is equivalent of changing just the initial condition, right? So let's just have an initial condition being mostly 0. I'm not really good at drawing that, and somewhere non-zero and back to 0 again. Now when I release my pen, what do you think, how do you think the solution is going to evolve? Which part of the solution is going to be non-zero? Okay, have your guess and go. I'm sure many of you have already envisioned that the solution is just going to move at vect towards your right without changing its shape, right? So if initially there is only a small spot of the solution not being 0, in this space-time diagram, which part of the solution is going to be non-zero? Some people are drawing using your fingers. Can somebody come and actually tell me, draw on the screen on this diagram, which part of the solution is going to be non-zero? Don't have to use your fingers to draw in the air. All right, please. Right, so if you look at the solution we just had over, well, did I type something? Oh, okay. Yeah. This you can draw on this one, which part is going to be non-zero.
I would imagine like you. No. I don't know.
So if I make a perturbation in the black dot over here,
yeah,
is all these lines you are drawing going to be non-zero regions of the space-time diagram?
More I don't know, like, because like there are some times that are like other than the perturbation that are like non-zero, because like after you introduce the perturbation, certain regions are non-zero. So like then at a higher t, your perturbation of the x domain is moved.
Yes,
right?
it's moving towards which direction? Towards
Positive x and
right,
positive t. So that's described by like a line.
Right. Okay. Very good.
Which is like a characteristic
of this equation. Thank you. So very good. So initially at t0, only this point is going to be non-zero, right? So basically everywhere else is going to be 0 except for this point. And the non-zero region stays as small as initial, but the location is going to be moved. At a later time, the place originally was non-zero is actually 0, and the non-zero region is going to be over here, right? So, and even later it's going to be over here. So the non-zero region is going to be a single line that extends from the initial perturbation at an angle. So it's very different from the domain of influence of either parabolic or elliptic equations, right? So instead of like a parabolic equation where there is a large region after the t0 that is going to be influenced, this we only have a narrow region that is influenced by the perturbation. Well, in general, for hyperbolic equations, we observe phenomena like this. There are certain characteristic speed of propagation of information. Here, information propagate, perturbation propagate at a finite speed. And the speed over here is actually u, right? So basically, after time is increased by a unit of 1, the wave is going to be moved. So let's say this is t0 plus 1. The wave is going to be moved by a x0 plus u, because u is actually how fast the wave propagates. All right. And in some more complex hyperbolic equations, there is more than one speed of propagation. There may be several different waves. A wave going towards the left, a wave going towards the right, maybe more than even 2 waves. But like you always have finite speed of propagation. There is nothing that is going to travel at infinite speed, as opposed to in parabolic equations like heat equation. Information is actually going to travel at infinite speed. All right. So that's for hyperbolic equations.